So we're looking at data types. It's an important topic in software design because data types becomes the core of everything that you do when you're programming. When we look at data types, we need to think about why we have to worry about this. And the first thing we need to think about is how is all data stored in a computer-based system? And I will apologise here, by the way, this is a very wordy presentation. I couldn't make it anything different. So how is all data stored in a computer-based system? It's really simple, stored in binary, because CPUs are made of transistors. Transistors have two states, charge or discharge, 0 or 1. Because of this, all data in a computer system, whether it be the text that you're typing, whether it be the operating system that you're loading, whether it be the desktop that you're running, or the game where you're firing bullets at your enemies, all data is stored in binary. And just so that you can see what it looks like in terms of electronics, we have a circuit diagram of our transistor. So we have our voltage in, voltage out, and they can be charged, discharged, and that voltage out can give you the values of 1 and 0. That's just a cute little picture. Don't have to worry about it too much for the time being. All right, so we've got to start thinking about how can we represent data, in this case integers and numbers, in binary. How do you convert a decimal number to a binary number? It's not actually difficult. Here's an example for you. And yes, this was hand-drawn. We have our binary number line. So what I want to do is convert that binary number 110111100 to its decimal equivalent. And it's not particularly difficult. Start by drawing the number line. So across the top, 1, 2, 4, 8, 16, 32, 64, 128. If you were to continue that series, what would be the next number?
256.
And then?
512.
And then?
1024.
And then?
2048.
And then?
4096.
And then?
8,192.
Come on.
I think that's about as far as I can go.
16,000 something, 32,000 something, that's exactly right. All right. So we're just doing powers of 2. 2 to the 0th, 1th, 2th, 3rd, 4th, 5th. Someone's going to go cringing at me soon. And it's extremely simple, okay? This is not rocket surgery. Wherever you see a 1, you add that decimal value. So there's a 1 under the 128 value. So we have one lot of 128, plus one lot of 64, plus one lot of 16, 8 and 4. And when you add it all up, that binary number, 1101100, is a decimal number 220. That's how easy it is to do. So I would normally take a whole lesson to teach you how to do this. I can do it in one slide, I think. So any decimal number can be converted to its binary equivalent and backwards by working through that. You start with that number line and go from there. I will give you some examples in a minute or two. Let's have a look at this now. This one's more complicated. Computers also use hexadecimal, which is base 16. So keep this in mind. Base 16 is called hex. And oftentimes, you know when your computer does a blue screen of death, you get a bunch of numbers on a screen and it gives you a random memory dump? That's the memory addressing in hex, because 1s and 0s tends to be a lot like the matrix. You really can't see it in anything other than code. Whereas hexadecimal, because it compresses the numbers down a little bit, it makes it a bit easier to read. Now, the way hex works, again, really simple if you think about it logically. We have a binary version of a number, and it's always going to be a 4-character binary version when we're playing with hex. And we have its hex equivalent. So 4 zeros, and you'll notice that all the way through here I put the leading zeros in. 0000 has the hex equivalent of 0. Funnily enough. 0001 has the hex equivalent of 1. You know, it's not brain surgery. 0010 has the hex equivalent of 2. Carrying on. And so therefore you can see 0111 is 7. Yes, that's a 7. I know it doesn't look like one. My handwriting is terrible. Binary version 1000 is 8. 1001 is 9. And then we run out of numbers because we can't get to 10 yet until we get to 15. You'll figure it out in a second. So therefore what we do is that we borrow numbers, or we borrow letters to continue our numbering system, because our Arabic numbers only go from 0 to 9. That's all we need. But we need to get to 15, or we need to get to the 15th value before we get to 10. So 1010, which is the decimal equivalent of 10, is the hexadecimal equivalent of A. And we steal the first 6 letters of the alphabet because we don't have anywhere else to go. Thankfully, we didn't go for Greek letters. So A, B, C, D, E, and F. And so 1111, 4 ones, decimal equivalent of 15, hexadecimal equivalent of F, binary equivalent of 1111. And we can use this table, and again, I'm going to give you exercises later on to work on. We can use this table to convert numbers between hexadecimal and binary, and therefore also decimal. Here's an example. 3A in decimal. So, 3, we've got to think back. Let's go back to the previous slide. What's 3? 0011. What's A? 1010. So 3, 0011, A, 1010. Can I convert that into its binary, into its decimal equivalent? Yes, I can. I've got 1 out of 2, 1 out of 8, 1 out of 16, 1 out of 32, it's 58. Okay? It's really easy. Now, we'll come back and do some more exercises on that. That's by way of explanation. Let's carry on. Let's represent characters. If you're worried about that, be prepared to have your mind blown. There are many ways to represent characters. The most common is ASCII, American Standard Code for Information Interchange. Do you need to know what ASCII stands for? Oh, heavens no. Do you need to know what it is? Yes. Every character you can produce on a standard keyboard, and look at the keyboard on your computer. That's a standard keyboard. It can produce, I think, 107 characters. There's a few extras in there. They all get designated a value in ASCII of 7 zeros to 7 ones, or everything in between. There is also Unicode, Universal Code, which gives you more variance. There's Unicode 8, 16 or 32-bit. If you have 32-bit Unicode, you can produce 2 to the 32nd power. Todd, how many is that? No, don't work it out. 4.2 billion, trust me. You can produce 4.2 billion different variants, which means you can produce 4.2 billion characters, which means you can produce every character in every language and every variation of every character in every language. Upside, lots of characters. Downside, more storage and more processing required. Here's an example of the Greek letter, small letter omega with a perispomene. I have no idea what that is. Perispomene. It's a little wiggle thing on top of it. Now, what I'm actually showing you here is this, and I'm hoping I'm recording the characters. So this here, U plus 1FF6. Now that tells us the Unicode version of it in hexadecimal. That gives us a hex code for that character. It also tells us something else. This is UTF-16. How do I know? I've got 4 hex characters, each of which is 4 binary bits long. So 4 times 4 is 16. So this is UTF-16. So Unicode 16, if you like, which means that there are 65,500 characters in this font. And I just picked one random one, particularly looking at this down here, the Unicode, which is pretty cool. Okay, moving on. Now, let's go and have a look at ASCII. This is one version of the ASCII table, and this is actually the one you probably need to look at first and foremost, because the syllabus says you need to be able to understand letters, characters, Unicode, not Unicode, sorry, their ASCII equivalent and conversions between. So if we look in here, let's look at the number 0, the character 0. Its decimal value is 48. You always thought 0 equals 0. You're wrong, 0 equals 48. Its octal value is 60. I actually haven't discussed octal with you, but if hexadecimal is 4 ones and zeros, octal is 3, it's base 8. We'll worry about that next year. And its hex equivalent of 0x30, so hex equivalent of 30. So what we can do is we can turn this character 0, it's 48 in binary, so we can turn 48 into a binary number, and that will be the key press for that character. When do you need to know this, by the way? Well, you need to know this when you're coding keyboard presses, key ASCII events. So, you know, a lot of games use WASD. Well, what's W? Let's go and have a look for it. There's W, 87 or 119. What's the difference there? The capital. And you ignore the 6th data bit. So basically, you code key ASCII event when key ASCII 87 or key ASCII 119. So it doesn't matter if your caps lock was on. And if you look, 65 to 97, look at F. 70 versus 102. There's always 32 bits difference between the upper and lower case. So that's a really handy table. It's also a really complex table. And it's just showing you the relationship between key press characters, hex, octal, and binary equivalents, although the binary is not actually displayed there. It shows that relationship between the data bits. Really useful for you when you're coding a keyboard to work. Let's move on quickly. ASCII does have many, many, many limitations. For example, it can only represent English, which is actually American characters, on a standard keyboard. And that was because it was invented in America. A point in sight. The Japanese, for all their wizardry with electronics, have not yet invented a keyboard that's workable for Japanese language. No, the Chinese. And because they don't have a language of a small number of letters, they have tens of thousands of characters. So your Chinese keyboard, if it was to be a proper Chinese keyboard, would be the size of this wall. And I want that one there, and then that one over there, and that one down there. And it would take you a long time to do anything. ASCII, this is actually not a limitation of ASCII, it's a limitation of the file allocation or FAT file format. FAT file systems, whether FAT12, 16 or 32, can only read ASCII. So if you have a file encoded in, named using Unicode or using a different file format, a different naming convention, it will show up as blocks. Now this will occur, for example, if you're downloading files that are named in Hindi, using Hindi characters, they may not turn up properly on your USB. They may show up as a block of squares. And that's because your USB can only read FAT file systems. Sorry, your USB is formatted FAT and therefore can only read ASCII. ASCII cannot render characters in other languages. Unicode, on the other hand, can render characters from other languages using 16, 32 or up to 48-bit representation. Normally you use Unicode 16. Unicode file names can be rendered in Unix and Unix-like, which is to say your Mac OS. Can also be used in NTFS and has been developed, rendered in exFAT as well, which is for your big hard drives. In other words, Unicode is far more flexible and far more universal. So let's have a look at some data types. Yay, integers. An integer is a whole number, very simple. No decimals, greater than 0. 0 or greater, actually. Right, this is an integer, a whole number greater than 0. Compare that to others, we'll find out shortly. We'll see why that's got to be declared like that. It is dependent on size when you're declaring a variable. For example, int 8, when you declare a variable int 8, it will be between 0 and 255. That's its minimum and maximum value. Int 16 will go between 0 and 65,535. Trust me. Int 24 will go between 0 and 16.7 million. Yes, okay, int 32 will go from 0 to 4.2 billion. Int 48 goes a long way up. Whether you need it's a different story. When we declare in C#, we will declare int 16 variable name equals 0, which is telling us in that expectation there, we're declaring the name, the size, and the value of that variable in one hit. So integers are just whole numbers. It's really simple. Next one, a string. A string is a text-based variable. They're used to declare names or other text-based things, obviously. For example, string variable name equals std. Really boring stuff there. Where would you use a string variable if you're coding a game? If you want... UI? Press E. Press E for stuff? It could be. But it would also be, for example, if you want to personalise your game. So when you start your game, what is your name? Nathan. Excellent. Hello, Nathan. Welcome. And that would be a string variable. Anything else you want to store in text as well. Now, before I said integers were whole numbers greater than 0. Here's another type of number, a floating point or a real number. A floating point allows for decimals, negative values, very small values, or very large values. These things are impressive, and we learn lots about them next year in the option topic. They're very cool, and they always follow the same structure, and here it is. It's a IEEE standard. So the IEEE, if you don't know, is the International Electrical Engineers Union. Don't know why it's an E instead of a U. But it's the IEEE 754 standard for floating point operators. Always, this is single precision by the way, always 32 bits long. There is a sign bit, a 1 or a 0 for positive or negative. An exponent, for those of you who do science, you know how you use scientific notation, 6.023 times 10 to the 23rd. Right, the exponent there is a 10 to the 23rd part. And that number, by the way, for you chemistry people is Avogadro's constant. And the mantissa, 23 ones and zeros. And because your exponent can be very, very big or very, very small, we can render an exceedingly little number or an exceedingly huge number up to 10 to the 300th, by the way. That's how big it can go. Sorry, 10 to the 120th. It could also go 10 to the minus 120th. It can be an exceedingly small number. And a 23-bit mantissa, lots of ones and zeros, means that we can have an extremely accurate number. In short, these things are awesome. We'll learn more about it next year, but what we're saying here is that we can declare a real number as a floating point so that it will allow for decimal values, so fractional values. They can be extremely huge, they can be extremely tiny, not both at the same time, by the way. You know, if I have 10,423,817.00000000001, who cares about the decimal? I've got such a huge number there, that decimal point is insignificant. Right? So I can have extremely big numbers, extremely small numbers, extremely accurate numbers, and more importantly, fractions. Boolean numbers or Boolean values. These are awesome. These are logical values. So Boolean variables are defined by logical parameters. For example, just so we know, they're invented. I am not from New Zealand, sorry Kiwis. Invented by an English mathematician called George Boole. Very smart guy. Now, important thing about Boolean logic, it is the base of logic gates and defines how all electronics works. This includes CPUs. And here is an example of one. I nicked this from some company, I can't imagine who it was. And if you look, the X and the Y in the little g are turning on and off, and we're seeing then through the rest of the logo what is true and what is false based on this. So when X and Y is on, the big G, X and Y, is lit. When the X or the Y, or both for that matter, is lit, the X or, so the yellow O, is on. When neither of them is on, it's not on. So that's X or Y, it's a logical value. The L, not Y, when Y is not lit, whether it's the X is on or nothing is on, not Y, is true. When the X is off, whether it be the Y is on or they're both off, not X is true. The interesting one here is the first O, XOR. It's called XOR, exclusive OR. X exclusively or Y. In other words, one or the other but not both. You can see the logic that's going on here, and this is the logic invented by George Boole that runs most electronics and certainly runs our computers. When we start playing with logic gates later on, this is awesome. So you can you see the way it's working there? Very, very cool bit of logic going on. So again, X and Y on, the big G is up because X and Y need to be switched on. That would be like a, in electronics, a series with two switches in series. Have a battery source, a light globe, and two switches in series. They both have to be on to turn a light globe on. The OR is where you have the switches in parallel with each other. One or the other is on, you complete the circuit so you can continue on. I can't do a circuit for exclusive OR, I don't know how to. It's pretty cool though. So that's not bad. That's a lot of fun. Thank you, Google. I may not, by the way, have sought permission to use that GIF. Bad me. Okay, let's have a look at Boolean variables that we code with. When we declare a Boolean variable in C#, it's very simple. Bool found equals false. Found is the variable name there, and its value is set to false. From there, we are telling the program that while we can tell the program that while this variable called found equals false, do stuff. Or we can do stuff until found equals true. And you'll see that coming up when we start looking at some of the searching algorithms. While found equals false, do all this stuff. Or repeat until found equals true. So hopefully when the algorithms tutorials come up, we'll see that showing up there. Now, there are limitations of data types. I'll give you a scenario here, okay? A really simple one, and I want some input from you. Let's say you are programming your game with a high score variable. The code to declare your variable is this: int 16, high score, equals 0. So you are declaring your variable as an integer. You're declaring its name to be high score and its value to be 0. So far, everything is excellent. Then a player comes along and sets a high score of 70,000. What happens? Yo. The integer variable, 16-bit variable, is too small to allow for a high score of 70,000. Congratulations. That's exactly right. So what happens here is a Stack Overflow. You fill the variable size and your program will try to write data beyond the end of the variable, which means it's going to write data outside its area where it can. Stuff breaks. Now, for those of you who ever owned a Nintendo DS or a 3DS, you may have had those SD cards or those memory cards that had 2,000 games on them. Probably not legal. They all worked on actually a Stack Overflow exploit. They found a game that you could write data beyond the level, beyond the point of the variable for your high score, which then could execute its own code, which then overran the DRM built into the 3DS. So just quick show of hands. Who's got one of those DSs that can do that? Yeah, they work on these exploits. So when I tell you that Stack Overflows can be quite narky, they can. This is also where a lot of exploits in Windows and operating system code come in, because you can write a variable beyond the level of the variable's value, which means you get outside of the code area that you're supposed to be working in, and you can do whatever you need to do. So these are not just a little bit of fun for your DS. These are really serious, and these can cause a lot of problems with your operating system. So when you see your Windows updates, someone's found one of these bad boys, and they're trying to sort it out. Okay, quickly have a look at this. A one-dimensional array. We've seen these before. A one-dimensional array is a single variable that can store multiple values. You have met these before. For example, in Yahtzee, we declare a variable called dice5. The 5 means it's a 5-element array. Told you that. And all data in an array, or in an array, must be the same data type. Now, if I'm lucky, what I've got here, we need to understand some properties of our array. So once again, my dreadful handwriting. Here's my int dice5. I have an index value, 1, 2, 3, 4, 5, which is the position in which I'm storing data, and I'm also storing the value. So in this case, dice4 equals 3. Can you see that? Dice4, the fourth index in the array called dice, has a value of 3. Yes? Which means that from there, I can say, well, dice5 also equals 3. Dice3 equals 6. Get where I'm going? So there's two values there that you have to be aware of, and you have to be able to work within them. The index value, which is a place that it holds is a place in the array, and also the value held in that place. That's interesting. Why did they do that? Here we have a record. A record is used basically to store data in a database. Sorry. So, records are used to store data in a database. We've all met databases before, haven't we? Has anyone not met a database before? Oh, good. Records can store data in multiple data types. And we've seen this when we play with databases before. Records will need a unique identifier for each individual record, which we usually call a primary key. So this is nothing new. This is just how we play with databases. An example is, I hope, coming up here, the use of records in a sequential file. So what we have now is a sequential file to store different data. Here's a structure. First name, comma, last name, comma, address, comma, suburb, comma, postcode, comma, home phone, comma, DOB, date of birth. Now, the commas here are important. So this is the structure of my data. First name, comma, last name, etc. When I go to throw data in there, here's what it looks like. John, comma, Smith, comma, 24 Callang Avenue, comma, St Mary's, comma, 2760, comma, 96238 comma, 01-04-2000 for date of birth. In other words, first name, comma, last name, comma, address, comma, suburb, etc. The separations there with the commas are really important. The second record, Rachel, comma, Murphy, 126 Beale Street, Easter egg in there, 126 Beale Street in Memphis is the Hard Rock Cafe. Yes, I looked it up. Sad, I know. Okay. So in this case, we still have first name, last name, address, suburb, whatever. This is called comma separated values. A comma separation is a type of a sequential file, which means I can have, if I have the same structure with lots of files, I can read through them, bang, really easily. Go to the 54th record and read after the third comma, I'm getting the suburb. Okay? And you can also have two commas, which means there'll be an empty field. Another sample way of looking at this could be, we've met this before, this is the data structure of a database. So first name, last name, whatever. Oh, and that's the end of my presentation. So there's a heap of stuff in there. I'm going to throw more work at you and more examples because I know that's a lot very quickly.